Video 6-5, VSEPR Theory. Okay, so what is VSEPR Theory? Well, it simply stands for Valence Shell Electron Pair Repulsion Theory. Okay, so what does that mean? Well, this basically helps you predict the shape or the actual arrangement and the bond angles, okay, of a molecule or a polyatomic ion. So the idea is that the valence shell electrons, meaning either bonds or non-bonding electrons, repel each other. Okay? And they don't like to be next to each other. So it causes them to align themselves that they are going to be as oriented as far apart as possible. Okay? Think of it basically as like a bunch of little kids in a house. They don't like each other, so they go to different parts of the house. You want to be as far apart as possible. Okay? Now, when we're dealing with this, we only need to worry about the electrons that are around the central atom. Okay? So you need to know the Lewis dot structure and what does the bonding look like around the central atom. Okay? Now, bonds will actually want to get further away from non-bonding electron pairs than they will from other bonds. Okay? So they will actually be willing to get a little bit closer to another bond if that means they can get farther away from a non-bonding electron pair. Okay? So as a result, the bond angles actually get smaller than what you'd expect them to be. Okay? Now, notations for drawing a structure. Okay? So let's say we want to draw this structure, XY4. Okay? And you drew the Lewis dot structure and you said, well, it comes out looking like this. X in the middle, Y's. Okay? Now, this may or may not be the actual structure of it. Okay? But if we want to show what it actually looks like in 2 dimensions for a 3-dimensional object, we do it this way. Okay? If it is a solid line like that, basically means it's in the same plane as your paper. Okay? So all 3 of these atoms, the 2 Y's and the X, are basically just lying flat. Okay? Now, let's say one of these Y's was sticking out of the board. So what you do is you draw a narrow triangle and you shade it in. Okay? So this basically means it's coming out. Out of your paper. Okay? And let's say one of these Y's, this Y was actually going behind the paper. Then what you do is you draw it as a dotted line, the bond. Okay? And this basically means it's going behind the paper. Okay? Now, what's the actual names or shapes that we can have? Okay? Well, you have to think in 3 dimensions. Okay? If you only had 4 pairs of electrons, is this the furthest apart that they could get? The 2 bonds. Is 90 degrees the furthest apart they could get? Okay? So, think in 3 dimensions. So, look at the pairs of electrons. You have to draw the Lewis structure. If you draw the Lewis structure wrong, your shape's going to be wrong. Okay? Look at pairs of electrons. So, pairs, don't forget, includes bonds and also non-bonding electron pairs. Okay. Now, double bonds and triple bonds, even though this is 2 pairs and 3 pairs, they only count as 1 single pair because they're all acting in the exact same direction. Okay. So, 5 basic geometries. Make sure you remember the names for them. Okay. AX2. So A, X, and X. Okay. You got 1 pair, 2 pairs. Maybe one's a double bond, maybe both of these are double bonds, maybe one's a triple bond, one's a single bond. Okay, but in essence, there's 2 pairs. Now, maximum separation you can have these 2 pairs is going to be 180 degrees. So it will actually form a straight line. Okay, AX3. So you have A surrounded by 3 pairs of electrons, 3 bonds. Okay, one of these could be a double bond also. That's why you end up with an octet. Now, if you got 3 pairs, if you're thinking in 2 dimensions or 3 dimensions, the basic maximum angle that you can have is going to be 120 degrees. Okay, so these 4 atoms basically end up forming a triangle. So we call this a trigonal planar molecule. Okay, all 4 of them basically just lie in a triangle. Okay, X is out here, and the A is in the middle, and they're all flat. Okay, now AX4. Okay, the shape of an AX4 is not going to be like this. If you think in 3 dimensions, you can actually get these to be greater than 90 degrees. So that's not the correct shape. Okay, the correct shape is actually something called a tetrahedral. Okay, 109.5 degrees. A tetrahedral is basically like a triangular pyramid. So what happens? A is in the middle, and you have the shape that I just showed you guys. One goes up here, one goes down here, one comes out of your paper, one goes behind the paper, and every single one of these angles is 109.5 degrees. Okay, now AX5. Okay, this is something known as a trigonal bipyramidal shape. Now notice, if you got 5 bonds, you actually end up with 10 electrons. Okay? Now remember, some atoms can actually make more than an octet, so have more than 4 bonds. Okay, so the shape of this looks like this. One up, one down, one like this. Okay, now one is going behind the board or your paper, and one is coming out of the paper like this. Okay, the bond angles between all of these are 120 degrees. Okay, so these 3 atoms, 1, 2, 3, are making a triangle, and they're perpendicular to your paper, coming out exactly 90 degrees. Okay, and the other 2 are straight up and down. Your 90-degree angle is between this one and this one. Okay, and your 180-degree angle is basically between the top and the bottom. Okay, so all of these are 90 degrees to each other. Now, you can actually have something called AX6. You can actually have 6 atoms bonded to a central atom. Okay, and this is an octahedral. Okay, what's it look like? Whoops, it should be A, X, 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 X. One is coming straight out at you, and one is going straight back. Okay, it's basically a square, 2 square pyramids on top of each other. Okay, now we get more variations based on those basic shapes. If one of those bonds is actually replaced with a non-bonding pair. Okay, so AX2E. Now, this is basically AX3. Okay, you have 3 pairs of things, but one of the X's is replaced with a non-bonding pair. So it still has to reflect the basic shape of AX3, which was our trigonal planar. Okay, but now we get rid of that, and you can't just say, oh, now it's just AX2. This still acts as an electron pair. Okay, so it still has to retain the basic shape of that trigonal planar. But since we now only have 3 atoms, okay, it's a bent shape. Okay, now, if you have 3 atoms, there's only 2 options. They can either be in a straight line, in which case it's linear, or they can be like that, in which case it's bent. Okay, now, the bond angle on a trigonal planar was 120 because they want to get a little bit further away from that electron pair. The angle actually gets less than 120. Okay, AX3E. Notice three things plus another pair. So that's basically based off of AX4. So we have to draw our tetrahedral. Okay, and then take off one of these bonds and replace it with an electron pair. Okay, so this is known as a trigonal pyramidal. This is above the other three down here. Okay, and the bond angle, it was 109.5 on a tetrahedral. These angles actually want to get a little bit closer because they're getting further away from the electron pairs. So it goes down to 107. Okay, now AX22E. This is still based off of AX4. Okay, you got two bonds and then two more electron pairs. So we still have four pairs of electrons. So it's going to be based off of this shape again, but basically now what happens is down here and up here you had electron pairs instead of bonds. Okay? And again, we got three atoms, so you only got two options on three atoms. It's either linear or bent, and this is going to be bent. Okay? And the bond angle, because both of these bonds are trying to get away from those electron pairs, they get further away. They get closer. So the bond angle comes down to 105.5. Okay, AX4E. This is based off of AX5. Okay, four bonds plus another pair. So, question is, this is AX5. Which one of these atoms should I take off? Okay, well, if you take off the top one, you have a 180-degree bond angle. If you take off the top one, that's gone. And you don't want to lose the biggest angle. Okay, so you can't take off the top or the bottom. So the ones that you take off is going to be one of these. Okay, and it gets replaced with an electron pair. This shape is known as a seesaw. Okay, where did the seesaw come from? It basically looks like this. If I rotate this, let's say 90 degrees that way, then that X go there. Okay, you have one leg sticking out this way, one leg going behind that way, and that's your seesaw. Okay, that should be about 120 degrees, maybe a little bit less, and between here and here, that's 90 degrees. Okay, and you still got your 180-degree bond angle. Okay, now, AX4-2E. Okay, so this is based off of 4 plus 2 more electron pairs. So this is AX6. Okay, now AX6 was the octahedral. Okay, now which ones do you take off? Doesn't matter which you take off because every single one gives you the exact same shape if you take off one. So let's take off this one. Okay. Now, when you take off the second one, you want to take off one on the opposite side, so that one goes away. Okay. So basically what you're left with is a square. Okay. And your bond angles are going to be 90 and 180. Okay, so try a little practice and we'll go over these in class. Okay, figure out the geometries, the shapes, and the angles for these things. So first thing you do, draw out the Lewis structure and figure out which shape is it based off of. Okay, so we'll do a simple one. We'll do water. Water's Lewis structure looks like this. Okay, so how do you do it? Well, figure out A is your central atom. 2 things bonded to it, so that's AX2. Those are your X's. And I got 2 pairs of electrons, so that's AX2 2e. Okay, now AX2 2e, if you go back and look in an earlier lecture, this basically meant it was bent. So you have to draw this as a bent shape. It was based on the tetrahedral shape, 109.5, but we just told you when it's 2e, it goes down to 105.5. And finally, the review question. What effect will non-bonding electron pairs have on adjacent bond angles?